Hello, my name is Sergiy Migdalskiy. I'm a programmer at Valve. I'm going to talk about performance optimization strategy. This is a 10,000-foot overview of the little things that make big impact on performance. I will never forget my first computer. Like a Soviet reality behind my window, it was very austere. It didn't even have a real keyboard. Felt really fast, because there wasn't much I could do with it. ZX Spectrum was my first user-friendly computer. It had basic interpreter and a real keyboard. And it wasn't fast enough, because there was a whole lot I could do with it. Spectrum had an 8-bit Xilinx CPU. This is it. By the way, you can make out individual transistors here. With just 8500 transistors, you can have a fully functioning CPU. A lot has changed. Pentium had millions of transistors. Some versions of Intel's Haswell or AMD Bulldozer have over 1 billion. Tip of a pen in this picture could fit 100 Xilinx, at least if somebody fabricated Xilinx in a 22nm process. This is how tough we used to have it. This is a floating point multiplication routine for Xilinx. It's not even full floating point. It ignores the least significant 8 bits. This is how easy we have it these days. This is how we multiply full float. In fact, we can also multiply quadruplets or octuplets of numbers the same way. Lots of things got simpler and better since then. And how do we use this tremendous power? Here is a virtual function call. It may cause 3 cache misses. When we fetch the object pointer, then the vtable pointer, and then the pointer to the function. That's before the actual function is even getting called. And to boot, you could miss instruction cache or TLB. This is the scope of the problem. Each car is an instruction here. A cache miss has to wait for main memory. And main memory is very, very far. It's 500 cycles away on the last-gen consoles. While this instruction is waiting, the rest of the program is waiting too. If I made this animation to timescale, it would take 10 minutes, and the virtual call can cause the stall 3 times in a row. This is how many instructions could have run if we didn't have a cache miss, 500. It's not quite the same on modern PC, but it's still bad. I'll talk about it in a minute. So why is memory so slow? Well, it's billions of capacitors, with just a few hundred lanes connecting them to the CPU. That's why there are layers upon layers of cache between them. The typical bandwidth nowadays is from 8 to 36 GB per second. It's usually shared between 2 to 6 cores and sometimes the GPU. It's not that slow if you use it right. But if you do miss the cache, the problem is the main memory is latent. CPU and RAM are quite fast, individually. But they're just far from each other. They can talk fast, they just won't hear a reply until later. It's like having a lag in your phone conversation. Chasing data down a chain of pointers exacerbates this problem. Every arrow in the chain is memory access, and it has to complete before the next can execute. The CPU asks for 1 cache line at a time and waits. The main memory delivers 1 cache line at a time and waits. Both CPU and RAM are basically waiting for each other most of the time. Everything should ideally be 1 pointer lookup away. Data dependency chains should be short. This will let CPU prefetch things in parallel. The out-of-order speculative execution engine will even do it for you automatically. I'll talk about it in a minute. You never read only 1 float from memory. You can only fetch the whole cache line. So use it all in its entirety. Align and pack your data into cache line-sized chunks. I have a rule of thumb that CPU should not starve, meaning it should not wait for memory. Here is a typical low-end machine. 2 GB per core per second and about 2 GHz. That's 1 byte per CPU cycle. I pack the data and then reuse it as much as I can before it's evicted from the tiny, puny L1 cache. Hopefully, pulling no more than 1 byte per cycle in the process. I estimate the cycles and bytes by hand. Well, I really count full cache lines in operations, but it's close enough. And I also measure and verify the assumptions, using all the tools I can get my hands on. One does not replace the other. Tools have poor signal-to-noise ratio, and estimates are error-prone. Always double-check yourself. Fundamentally, when CPU has enough stuff to do, it's easy to fix cache messes. It's good to be compute-bound. I can concentrate on optimizing the logic, and I can see immediate and predictable results. Classic computer science training prepares us for exactly this scenario. It concentrates on minimizing the number of operations to take things to next level. When you are compute-bound, that's exactly the right thing to do. If CPU doesn't have enough stuff to do, if you are not compute-bound, you lose ticks to cache misses, and this is how much per miss. With stalls of these proportions, no wonder performance is often so poor and unpredictable. I hope I convinced you that CPU cache misses are pretty bad. And wait a minute. The last gen consoles power PCs were dual issue. That's 2 instructions per tick. So it's more like we lost 1,000 instructions per cache miss. That's a theoretical number, but I did reach 1.6 average instructions per cycle in optimized code. Typical memory latency on a modern computer is about 50 nanoseconds, maybe 60. That's about 150 ticks on a 3 GHz CPU, not 500. In reality, it's longer because it takes time for CPU to realize the address is not in cache and send the query to memory. Also, other cores and GPU compete for the same memory lane, memory bus. That increases latency, but let's stick to the slightly delusional 150 ticks. That's much better than 500, right? Well, here is the thing. You can run 3 or more instructions per tick on Ivy Bridge CPU. Moves here are just registry names. It's kind of a cool shortcut on CPU. Moves cost almost nothing because they don't go through the whole CPU pipeline. They don't use execution units, at least on many of the latest CPUs. But the increments are real arithmetic operations. It's pretty cool we can run 3 of them per tick. So let's compare the old with the new. If you stall the modern CPU for 150 cycles, the theoretical opportunity cost is about 450 simple instructions. You'll never achieve 450, but you can get half of that quite easily. And in the last gen, it wasn't unheard of to run 2 cycles per instruction and not to worry about it. So the cache miss opportunity cost was about 250 instructions in the last gen and about 220 today. It's faster, but it's not cheaper today. So what about out of order, you might ask? Doesn't CPU just go ahead and leave the stalled instructions behind? The other instructions just running speculatively ahead? So any instruction stalled on a cache miss should just be reordered until the memory read is complete. Unfortunately, it doesn't quite work that way. Instructions are not all independent. You fetch data from memory because you need it, usually right away. So stalling one instruction stalls the whole dependency graph downstream. Like those yellow cars, they can't move anywhere. But what about those other instructions that don't depend on your memory data? Few other instructions can make real progress with some variable in unknown state. The reorder buffer size is not infinitely long. Haswell has 192 entries in reorder buffer. It also has limited number of other resources that can shrink the reorder window. So yes, sometimes it helps. To count cycles on modern superscalar architectures, you need to be comfortable with 2 numbers. This is familiar to most of you. Every instruction has latency and throughput. Latency is how many cycles it takes for a result of one instruction to be available for the next. Latency of 4 means you can't use the result of the instruction until 4 cycles after it issued. Throughput is how often the instruction can issue. For example, if a multiply has 4 cycle latency but throughput of 1, You can issue one multiply every cycle as long as they are independent. If throughput is, for example, 1/2, it means you can issue half an instruction per cycle. In other words, you can issue only every other cycle. It's kind of quirky terminology, so sometimes people use reciprocal throughput. Throughput of 1/2 is the same as reciprocal throughput of 2. So every other cycle. The compiler tries to schedule instructions from other dependency chains after an instruction with high latency. Latency and throughput numbers in CPU documentation assume the best case. There are a lot of hazards that can make them worse. Here is an observation. Instructions depend on each other. You cannot compute the length of a vector until you fetch the vector from memory. You cannot divide it by length if you haven't computed the length yet. Instructions form a dependency graph. The edge length in the graph is latency. The longest path is the dependency chain that limits how fast you can execute this graph. The latency becomes huge if you have cache miss. It can delay the whole program. But at least you have many short chains that can run in parallel. The CPU can reorder the cache miss and get some work done. And if you have 2 misses in 2 parallel chains, chances are the CPU can fetch both cache lines at the same time. That's huge savings. Even if you have few short dependency chains, but they all miss cache, the CPU will simply run out of reorder buffer, or reservation stations, or register names, or some other resources and stall. Sure, it'll wait for several cache lines at the same time, and for sure it's better than waiting for them one after another. But avoiding cache misses is still #1 priority. Say you fixed all your cache misses. Lots of short chains still work best. Optimizing compilers can schedule parallel dependency chains side by side. They do it extremely well. And shorter latency chains, and even individual instructions with shorter latency, are much easier to schedule. Compiler can reorder instructions at compile time. And at runtime, the reorder buffer has more instructions to choose from. This improves CPU throughput, because more instructions can issue in parallel. The more short chains are in a linear block of code, the better they can schedule and utilize the CPU. It was hard to hide latencies with in-order CPUs of the last gen. Some instructions had a latency of a dozen cycles. It's rarely an issue nowadays with short latencies and out-of-order execution. But exploiting and optimizing the multi-issue capability is much more subtle. In some very limited sense, having multi-issue is a little bit like having faster tick rate, and also slower latency and throughput. We still have to increase instructions per clock metric and avoid starving the CPU execution engine. But now, it's very hard to analyze the behavior of the reorder buffer. Here's another little fun insight that the GPU engineers shared with me. What's the latency of an add instruction? Is it like 1 cycle? Well, it depends on your perspective. Real-world CPUs fetch bytes from memory, decode instructions, issue and reorder instructions, execute instructions, retire instructions, put things into complex queues between all those stages, and do a whole lot of other things. A CPU obviously cannot fetch, decode, reorder, execute, and retire an instruction in a single cycle. It can literally take hundreds of cycles between the CPU sees this tiny little add and when it retires it, or cancels it, as the luck has it. The CPU is so heavily pipelined to do its very best to hide this dirty little secret from you. It's huge and latent. And this is what makes it possible to hide a lot of nasty stalls. This might also be why some of the prefetches you casually sprinkled around your code last time had little measurable effect. Which reminds me, prefetches are tricky. First of all, prefetch instruction is treated merely as recommendation by many CPUs. You can try to insert a memory load and compare instruction directly in place of a prefetch. Then CPU has no choice but to fetch the memory. But it's much better to structure the code and data for the hardware prefetcher. because it's hard to beat the hardware prefetcher. If your data is a linear stream, hardware prefetcher will work perfectly. Software prefetchers are unnecessary and sometimes even harmful in this case. If your data is random, prefetching early enough can sometimes help, but often it won't. For instance, cache misses are often overlapped with each other and with the execution. If you fix just one or two cache misses that happen in parallel, the other is still there, so it won't help performance. There are valid situations when you don't have enough work per byte. In those cases, you want to maximize system memory bandwidth. Because if CPU is idling, you don't want the memory bus to also be idling. If your memcopy is slower than 8 GB per second, then there is room for improvement. And by memcopy, I mean any task that is memory bound. And by 8 GB per second, I mean whatever is available bandwidth. Until then, you're just wasting resources. Something is very wrong with brainless memcopy-like jobs. CPU is essentially free when you are waiting for memory. You should do something with it. Sometimes you can compress data or join two jobs together to use CPU more. Tiling reduces memory traffic by utilizing cache better. On the flip side, memory bandwidth is free when CPU is too busy. But that doesn't happen too often. In short, I try to load balance CPU in memory. Prefetching is sort of like double buffering. You fill one buffer while working on the other. It works best when CPU prefetches for you. That works best when you use a couple of linear streams of data. Doesn't invalidate the simple fact of life. If you are eating bytes faster than they can be delivered, you starve the CPU. So my desktop computer is supposed to have the aggregate memory bandwidth of about 37 GB per second. But simply reading an array in memory goes at 13.5 GB per second, about 1/3 of overall bandwidth. Why? The CPU has bottlenecks, or spare capacity, depends on the point of view. One thread, two streams can go at 18 GB per second, half the system's bandwidth. Two threads, two streams go at 25, and many more streams go at maximum. They saturate pretty quickly. It's okay to split data into a few streams, and in fact, it may be beneficial. But don't count on every thread having access to the full system bandwidth. So what's the minimal bandwidth you should count on? Let's say we have the familiar low-end quad core, something like a Core 2 quad with DDR2 memory. It has 2 GB per second per core, which is exactly 1 byte per CPU cycle. You can usually run at least 1.5 instructions per cycle. In physics code, let's say that's one math instruction and half address or logic instruction. That means that if I count the bytes and count the math operations in my code, I want them to be in balance. If there's more data, I know I want to compress and pack it into fewer cache lines. It's okay to run more computations, but this is my ideal target. I try to keep it simple. Writes normally don't stall on modern CPUs. CPU can put a write into a queue and the queue is long enough. If you try to load data right after store, modern CPUs forward data from that store queue. On the last gen consoles, it always caused a stall. Not anymore. Unless you try to play tricks with unions and mix and match data of different sizes, you should have no problems. For example, if you combine two 16-bit integers into one by writing and then reading from memory, that may cause problems. It's a gotcha to be aware of. To write a byte that's not in cache, usually CPU fetches the whole cache line and only then writes a byte. So memory write can cause a cache miss or cache line migration from core to core. It doesn't stall, but it still pollutes the cache. It may be cheaper sometimes to do a few checks and not write anything out, especially if another core may be accessing the same cache line. You don't want to steal cache lines from another core. If your branch is random, it's fair to say it will mispredict half the time. So random branches are bad. All CPUs try to predict branches nowadays. Some are more sophisticated than others. Sophisticated branch prediction is not for us. mainly because it differs from CPU to CPU, and we want our games to perform well on all of them. Every CPU predicts slightly differently, but they all have something in common. If you have consistent branches, you'll have consistent prediction. When your conditional changes is when you incur the misprediction penalty. After 1 or 2 passes, it's predicted correctly every time. The 2 passes may be required because the branch predictors are too smart. Some will see occasional mispredicted branch as a fluke. Then they mispredict again, and then they'll switch their prediction to the correct one. But these are the details that distract from the big picture. You just don't want your branches to change their direction often. Predicted branch costs you literally nothing. And if branch always goes the same way, pretty much any modern CPU will predict correctly. Function calls and returns are very special kinds of branches. The return is a form of indirect jump, which is very hard to predict. And function calls happen very often. That's why on most modern CPUs there is a hardware optimization. It's called return stack buffer. The CPU keeps track of a few return addresses and predicts returns perfectly. So you shouldn't be afraid to call non-inline functions. It's really cheap these days, at least if you don't do any trickery that throws off the predictor. But you should be aware of recursion deeper than a dozen calls. If you blow through the CPU return stack buffer depth, each return may cost you a dozen or more cycles. Here is a specific example of how I measure performance and bandwidth. In a cloth solver, I have bulky cloth elements moving 16 verts at a time. It takes 600 clock cycles to run 1,000 instructions. The data is 5 cache lines streamed and 8 cache lines scattered gathered on top of it. That's 46 cycles per cache line, a bit worse than 1 byte per cycle. I'm still ALU bound, which is good. Optimizing math actually gives perf benefit. And perf is quite predictable. Unfortunately, it also means every extra math operation takes a bit slower. I'm consuming memory at 4.7 gigabyte per second per thread. That's enough to affect other threads in some limited cases. There's room for improvement, but I'm happy enough with these metrics and I move on, because my bottlenecks are elsewhere. I was asked how I measured the stats from the previous slide. It's actually very low tech. Even though I love profiling stuff with fancy tools, I still measure my loops with timestamp counter. Since I write my SIMD loops without branches, they always execute the same code path. So unless they stall randomly, the time per iteration is very repeatable. I just sum up all the cycles and all the iteration counts. This gives me the average cycles per iteration. I can derive a lot of useful metrics from that. In this case, I just carefully counted the cache lines by hand. It's not too hard because I organize my data in large aligned blocks. The 8 random access cache lines are there because I read and write 16 verts per iteration, and I can only place pairs of those verts next to each other into the same cache line. I assumed conservatively that all my data is called, meaning not in cache. And I also assumed ultra-conservatively that I won't hit the same cache lines with the randomly accessed vertices. This is actually wrong because I specifically optimized the order of computations to be cache-friendly. So the memory traffic of 4.7 gigabyte per second is probably overly pessimistic. For the instruction count, I just copy-paste the assembly and count the lines. I should really count micro-ops, and I can do that with Intel architecture code analyzer. Out of order represents an interesting compromise. On one hand, it uses real estate on the chip. Not a whole bunch, but some appreciable amount. So it reduces the raw throughput of the chip. But it also improves it by making better use of resources. In the real world, it's a net improvement. I don't want to spend my days poring over low-level engine routines. I want to be creative, and computers to handle mundane tasks. Out of order does just that. And it does that to the whole program, not just the hotspot loops. So it's very useful. So let me summarize. So far we covered that cache misses are expensive and just how expensive they are. You should always count cache lines, not bytes, for bandwidth computations. Out-of-order execution hides latency and pipelines everything, but we can help it by disentangling dependency chains. RAM is fast, but far from CPU. We can help it by laying out data for hardware prefetching. 1 byte per op rule of thumb for math-intensive physics code. Very useful. What's missing from this picture? How about a weird little trick that will let you lose 32 bytes in a day or less? You know what? I miss the simplicity of 8-bit times. A program used to always load at the same offset. Every variable was always at the same absolute address. You just bake the game binary, and when it loads, it's ready to play immediately. Not anymore. We allocate memory dynamically. We can't just bake pointers into the dark image, disk image. We waste 8 bytes per pointer, although we are really far from using all that address space. This is 10,000 feet strategic overview talk. But I wanted to share this technique that we use at Valve. It's a simple templatized class that behaves like a pointer, but is position independent, and it's binarily compatible between 32-bit and 64-bit code. We save these data to disk raw with all the relative pointers, then load them at runtime, and they are ready to go. Very simple, no fix-ups or decoding. Same data in 32 and 64-bit, and it generally doesn't cost any more than raw pointers to use. So how do we do that? There are two ways to address memory: directly with absolute address and indirectly relatively to another address. A normal pointer is the absolute address. Relative pointer is a relative offset from itself in bytes. You have a block of memory with relative pointers, save and loaded from disk, and it's still valid. The offset of 0 would point to the pointer itself. It's not very useful, so 0 is treated like a null pointer. We use this extensively to bake all of our physics collision data and load it at runtime, without multiple dynamic allocations or fix-ups. One natural limitation is that you have to move a piece of memory as one contiguous block. You can't fragment it. 32-bit offsets let you address plus or minus 2 gigabytes. Here is the implementation. We have an offset and overloaded operator arrow that just computes the pointer from the relative offset. Note that this doesn't result in a null if the offset is 0, so we assert in that case. But we do check for null in assignment. Just like with normal pointers, you shouldn't dereference a null. So to recap, in this big, huge address space, you have a sandbox. It can be model data, collision of the world, or nav mesh, or anything else logically belonging together. The sandbox doesn't have to be small. With 32-bit offsets, you can easily address within 2 gigabytes. You can also make the offset be in words, not bytes. Then you can make your pointers 4-byte aligned and address plus or minus 8 gigabytes. Anything can point to anything arbitrarily within the sandbox. Pointers are relative offsets and can take 4 bytes. You can also make some offsets 2 or even 1 byte. And you can make the sandbox very small. So this whole sandbox can be moved about arbitrarily. It can be dumped to disk and loaded from disk. All the relative pointers remain valid. The beauty of this method is that you don't need to write any serialization code. There is no need in any reflection API. It's very, very simple. We usually don't want to move the memory while we are constructing the data. It's inconvenient. On the other hand, we don't know in advance how much memory we'll need. So we do a virtual alloc, guessing how much data we may ever need, and commit it incrementally as we allocate more data. It works very well in practice, except when you want to compile 3 gigabyte texture on a 32-bit machine. Here is a little comparison chart of a linked list with normal pointers and offsets. the declarations are very similar. The pointers that point inside the data block change to offsets. We use the template class for that. All the data fields remain the same. Alignment and size can reduce. We have to use explicit allocator to stay in the sandbox. At Valve, we use a simple stack allocator. That makes data layout predictable and explicit. The assignment operator handles the null case. In all other respects, the behavior are the same. So the runtime class is just a few lines of code. The tool time allocator class is maybe 50 lines and has a call to virtual alloc, but it's still pretty simple. There's no runtime overhead. Byte offsets cost nothing on modern CPUs. Code gen and register usage is slightly different, but it doesn't matter in practice. The format on disk is exactly the same as in memory. You can even memory map files. The data becomes more compact because pointers aren't 8-byte large anymore, and is good for cache. There are some limitations, of course. Automatic versioning is important for data that you cannot reship or recompile easily. In practice, we use this for data that changes frequently and isn't easy to construct. So we can rebuild it often, but it can be arbitrarily complex structure and it's very efficient to load and reuse. The data structure must reside in contiguous block of data. It's less than ideal for constructing on the fly, but it is ideal for data that you load from disk and never change. It's an extra concept to learn for the programmers new to the code base. This is not a trivial consideration in large teams. So we talked about how CPU works and then about a weird little trick that will let you lose 32 bytes in a day or less. This is a talk about strategy after all. So what's missing is the bigger picture, some systemic approach with strong theoretical underpinnings. I wonder what that would be. See, back in the day, things were simple. CPU took an instruction and executed it. It had a manual that listed all instruction timings. I could predict with 100% certainty how fast anything could be. This world is gone. Unfortunately, there is no established theory for designing globally optimal algorithms on modern hardware. There's well-developed asymptotic complexity analysis theory, the big O notation. It's often uninformative if your data isn't infinitely large. There are also glorified tips and tricks and best practices that we learn and publish and apply. Those have no established underlying theory. Optimization is still half art, half science, and a pinch of magic. Obviously, any optimization effort should include complexity analysis early. You fix the algorithm first, count cycles later. CPUs work very non-linearly though. Adding an instruction may literally cost 0. The exact same operation may cost 200 cycles elsewhere. You can't just count instructions and be done. But nobody repealed the fundamental laws. Here is my favorite complexity, nada. If I don't have to do something, I don't want to do that. Cheat it. Talk to the designer. Chances are that not everything you do is absolutely necessary. Another of my favorite complexities is O1, for example. Cache the result, hopefully with O1 lookup. Memoization is another name for this trick. Do stuff once per frame. We were trying to optimize ragdoll creation in Left 4 Dead. After struggling with hitches for some time, we just queued up and staggered ragdoll creation. Fixed a lot of hitches and nobody noticed. Approximate what you can. Especially in game physics. It's all about approximating and simplifying the real-world physics into the ground. I'm sure we can come up with some sorts of cheap tricks, all of us. But if nobody notices, that's not a cheap trick anymore. That's a valuable technique. Array traversal and linked list traversal are both O in complexity. Does it mean they're the same? Linked list is certainly very cache unfriendly. But even if it's 200 times slower, it's still ON. Big O doesn't capture the constant, and on modern CPU, constant is very relevant. In the old times of 8-bit CPUs, there were no such nuances. It was in fact about as fast to iterate an array as linked list. It was popular and useful to compare algorithms by the flop count. Today, it can be very misleading. Here is an example of big O being misleading. What should we use, red-black tree or a hash table? Think about simple lookup in a map with 1,000 elements. In the classical variant of RB tree, you touch 10 to 20 cache lines. That's a lot of cache misses for lookup. That's also a lot of branch mispredictions, unless your binary search is branchless. Because the binary search branch is effectively random. Although if you insert in order, you traverse in order, it'll be cache friendly. In a classic hash table, you can have horrible hash collisions. They can make worst case lookup linear. But if you simply use sensible hash and bucket count, you can expect to touch on average 3 or 4 cache lines, almost regardless of the number of elements. And the branches are still inherently predictable. So what's more important, algorithmic complexity or cache misses? In the real world, the operation cost makes a big difference. Should you use CPU or memory? It's a judgment call. It's a trade-off between practical performance and theoretical or worst-case scalability or reliability. And we should pay more attention to cache friendliness of our algorithms. Instructions actually take different number of ticks, and that's fine. But if you don't know if a branch will take 1 tick or 20, or if a register load will take 4 ticks or 200, then you can't make good decisions about your code. You just make wild guesses. Eliminating stalls makes performance predictable and makes decisions informed. So suppose your algorithm is rock solid optimal. You have no cache misses because you prefetch everything perfectly, and your instructions pipeline well, and you never have any stalls. And suppose you are computation bound. There are a lot of such cases during physics optimization. What next? SIMD is an obvious next step. SIMD is by no means trivial to implement. It imposes a lot of limitations. Like you have to have multiple things to process at the same time. No big revelation there. And computations in different SIMD lanes must not affect each other. Even if you have 4 things to do, it doesn't mean you can do them in parallel. Like if you have 4 contacts to solve, they may affect the same rigid bodies. So you may have to decide how to blend the results together. SIMD doesn't have to be super hard though. I'll share an easy workflow that I used for the past 10 or so years. I start with a scalar path, keeping in mind the kind of things SIMD is good at. So I use no branches at this stage, for example. But I use reciprocal square roots, min, max, and selects very generously. And I process one thing at a time, but in a way that allows me to group them into groups of 4 or 8 independent things. So for example, one single rope solver would not be SIMDizable this particular way, because it only allows sequential computations. You need to be very deliberate with your data layout at the stage when you are planning SIMD. Or you'll have to load 4 separate elements and then shuffle them. That's worse than 1 instruction per element, which is worse than scalar case. In the nearest future, we'll all have special gather instructions. But I suspect it won't fix the problem completely, because fundamentally CPU will have to hunt down multiple pieces of data and shuffle them together. So it'll probably cost us latency. And when you save the data out, you have the same problem. You have to shuffle first and save data element by element. You can easily end up with SIMD code that's slower than scalar this way. You don't have to interleave the data right away, but you need to think about it early. Otherwise, it will be hard to lay it down correctly later. There's a glimmer of hope though. When code is scheduled nice and tight, you're usually bound to only one pipe or issue port. In physics, that's normally the arithmetic pipe. It's the U pipe on the older power PCs, or the issue port 0 on the newer Intels. And guess what? That leaves the other pipe or ports idling half the time. That means any additional instructions that can issue on the other pipes are essentially free. And those are normally the logical and shuffle pipes. Why is this interesting? Because even when you do math in SIMD with maximum throughput, you can still swizzle and transpose your data essentially for free on the other pipes sometimes, as long as you don't do it too much. Of course, you should never rely on your code being scheduled ideally tight. So your input data should be swizzled so that you load 4 elements with one load instructions, as much as possible. You can't always pack the data this way, but you should do it every time. You should put maximum effort into it. For example, you can swizzle and pack static model data this way pretty much always. You'll have to duplicate data sometimes. That's okay. RAM is cheap these days. It's the bandwidth that's at premium. Because the operations of loading, storing, and shuffling can pipeline well with computations, some gather-scatter activity can hide behind the math. The one node per byte rule is handy here. If you limit how much you load, you can also limit how much you shuffle. But it's still best to avoid as much as you can. The inputs and outputs of SIMDize algorithm are good candidates for gather-scatter, because it's usually unreasonable to build an API with interleaved structures. But when I have full control over design of data structure, an API is not an issue. I interleave the data as much as I can. After I do that, I replace all operations with their SIMD equivalent. This is the part where I actually start using SIMD operations. Sometimes I templatize code and data by type float. This function computes an approximate givens rotation. If you pass float 4 as a template argument, it will compute 4 givens rotations. I wouldn't recommend it if you are not very familiar with SIMD. Also, there is a tool that does it for you. It's called ISPC. I take the scalar data structures and I replace all types and operations with their SIMD equivalents. Float becomes 4 floats, and then int becomes 4 ints, and so on. And it just works. This is an example of scalar path versus SIMD path struct in a cloth solver. Of course, when you compute 4 of something in parallel, there better be no dependencies between those 4 things. It takes some forethought. Some problems are notoriously hard. For example, some matrix factorizations. And some are very easy, like this one. Here, one quad is solved per lane as a single block. Same with rods. I just make sure quads don't touch and rods don't touch. That's all. It works like a charm. So to SIMDize something, you need 4 or 8 items that need similar processing, and they must be independent of each other. There's a myth I've heard that SIMD is always a premature optimization. You shouldn't write SIMD right away. But when designing data structures and algorithms without SIMD in mind, it's hard to separate data into independent homogeneous lanes cleanly afterwards. If you don't do that cleanly, you have to waste time shuffling and preparing data, which destroys the benefits of SIMD. There's no easy recipe for SIMDizing 4 things with different computations. But there are a couple of recipes of how to handle branches. First is the most commonly used, and that's what happens on GPUs. If you have a condition, you execute both the if and else branches or for all elements, and then select one of them. Everything that's not selected is wasted computation, but it can easily be faster than running the scalar path with branches. Here is another branch trick. You just sort elements by conditional. One list for if, one list for else. You can even SIMD sort it 8 at a time without branches. Then you can run if and else code only elements that need it. No wasted computations. Obviously, the same caveats about ordering and dependent elements apply. This is harder to pull off, but it's much more powerful technique. You'll often get almost 4 times the perf with SIMD, or 8 times in case of AVX. That is, if your problem is separable, and if you lay out your data right, and if you plan for SIMD ahead of time, both for code and data. SIMDization is very problem dependent. Compilers are very bad at auto-vectorizing non-trivial code. It's very hard to SIMDize something that wasn't meant for it. or if the problem is not separable by itself. But 2/3 of CSGO players have CPUs with AVX support. So the future is bright for SIMD techniques. I'd like to extend a special thanks to my art team, which is 3D art by Anna Bibikova and 2D art by Heather Campbell. Thank you very much.